Okay, hello everyone in a new video. So we have reached part 2 of chapter 2, which is the chapter of electric voltage for grade 10 students. So in this part we will solve some exercises as a direct application on what we have explained previously and complete the explanation of this chapter. So let me start by exercise number 3. In the circuit whose diagram is represented in the adjacent figure, they mentioned the figure, then now we can use it. Okay, sorry. So they are telling me the voltage across the dry cell is UPN is equal to 4.5 volts. Then as we know, the trick in solving such type of exercises is to label on the diagram the given voltage. So UPN is equal to 4.5 volts. So this is given by 4.5 volts. But more than this, we need to label this voltage, which is given by UPN. So it is important that in addition to the value of the voltage to give the name on the diagram. And the voltage across the lamp L2, which is UCB, is equal to 2.1 volts. So here we have 3. Let me erase this. So here we have 3 electric components and they are given by the lamps L1, L2 and L3. We have that the applied voltage UCB is equal to 2.1 volts. Okay. Now in part A, they are telling me to determine the voltage UAB, which is VA minus VB. And this can be determined by applying the law of addition of voltages. So always in physics, we need to mention the law that we are using. So let's start as a title. Apply law of addition of voltages. So always on the left, we will write the voltage that we are interested in calculating, which is given by UAB. And on the right hand side of this equality, we will write voltages across different electric components starting from A and ending with B, such that we know the voltage across these electric components. So from A we'll go to the point P, from P we'll go to the point N, and N back to B. So UAP plus UPN plus UNB. So notice that we have started with A on both sides and we have ended with B, and each letter we have inserted it twice. Okay, so in this case across A and B we have a connecting wire. So here let's justify between brackets that UAP is equal to 0, and the reason is given by connecting wire. Why? Because previously we didn't justify why UAP is equal to 0. Now UPN is given by 4.5 volts, which is given. Now as for UNB, across N and B we have a connecting wire. So between brackets, let's say that UNB is equal to 0, and the reason is given by connecting wire. Now, what's the type of this equation? This is a linear equation in one unknown. The unknown is given by UAB, which is already placed on one side. So this is given by 4.5. Since 0, 4.5 and 0 are expressed in volts, recall that we cannot add or subtract or equate physical quantities unless they have the same unit. So in this case, the applied voltage UAB is given by 4.5 volts. And now let's label this applied voltage on the electric circuit. So we have that UAB is equal to 4.5 volts. Now in part B, they are asking me to calculate the voltage UAC across the lamp L1, and this can be done also by using the law of addition of voltages. So let's say apply law of addition of voltages. So always on the left we write the voltage that you are interested in calculating, which is given by the voltage UAC, which is across the lamp L1, then UAC. And on the other side of this equation we'll go from the points A and C such that we know the voltages across different electric components. Then from A we'll go to the point P, from P to N, and to B, and B back to C. So we have started with A, ended with C, and each letter we have inserted it twice. Then UAP plus UPN plus UNB plus back to C. Okay, so UAP is equal to 0 justified previously, UPN is equal to 4.5, now UNB is equal to 0 justified previously. Now UBC, notice that here in this case UCB is equal to 2.1 volts. We know that UCB and UBC are related via a minus sign. So in this case, this is given by minus 2.1. Now we have that 4.5 minus 2.1, and this is given by 2.4. Since both 4.5 and 2.1 are expressed in volts, so UAC will be expressed in volts as well. So the applied voltage UAC across the lamp L1 is given by 2.4 volts. And notice that here in part A, we could have answered UAB is equal to 4.5 volts because simply the terminals A and B are in parallel to the battery, and this is given by law of uniqueness of voltages. Now in part C, they are asking me to calculate the voltage UDE. We can say simply that D and E are parallel to the terminals A and B, so UDE is equal to UAB is equal to 4.5 volts. But in a more elegant way, let's solve it using the law of addition of voltages. So let's say apply law of addition of voltages. Always on the left we write the voltage that we are interested in calculating, which is given by UDE. And on the other side of this equation we go from D to E. So we will go from D to the point A directly to B because we know the voltage UAB to be given by 4.5, and from B back to E. So let's say UDA plus UAB plus UBE. So in another way we could have went from D to A to P, P to N to B, B to E. So both of them will give the same result. Now in this case UDA is equal to 0, so we didn't justify this previously. Let's say here between brackets that UDA is equal to 0, and the reason is given by connecting wire. Now UAB is given by 4.5 plus UBE is equal to 0, and the reason is given by a connecting wire. So in this case the applied voltage UTE is given by 4.5 volts. Now let's move to the next exercise, which is given by exercise 4. They are telling me the electric grid shown in the adjacent figure. They mentioned the figure, so now we can use it. It's fed by one electric generator. So notice that this generator is a DC voltage source from its symbol. The pole plus and minus of this generator are respectively labeled by P and N. Okay. The following voltages are measured. So for example, we can measure these voltages using an oscilloscope or a voltmeter. Then UAB is equal to 20 volts. Then the trick in solving such type of exercises is to label the voltages and their respective names on the given figure. Then we have that UAB is equal to 20 volts. Now as for UBC is equal to 10 volts. We have that UBE is equal to 5 volts. And UED is equal to 3 volts. Okay, now we are asked to calculate the following voltages. Let's start by UAE. And for sure we will do this using the law of addition of voltages. Then let's say apply law of addition of voltages. So always on the left we write the voltage that we are interested in calculating, which is UAE. So we are interested in determining the value of UAE. So on the right hand side of this equation, we'll go from A to the point E across different electric components such that we know their potential difference or their voltage. So from A we can go to B because we know UAB is equal to 20 volts, and from B we can go back to E because UBE is equal to 5 volts. So let's insert the point B, then we have UAB plus UBE. So in this case the value of UAB is given by 20, and the value of UBE is given by 5 volts. So this is given by 25. Since both 20 and 5 are expressed in volts, so the value of UAE will be in volts. So after we have determined this applied voltage, let me label it on the electric circuit itself. So we have that UAE is equal to 25 volts. So now here, the aim of this exercise is to determine the voltage across different electric components. So notice that now because we have determined the voltage across A and E, so we are expected to be asked about the voltage AD because now this is a closed loop. Later on they will ask us about the voltage UCD because across this loop we know all the voltages. Later on they will ask us about the voltage across the battery. Now indeed they are asking us about the voltage UAD. So let's say apply. Let me write as a title the voltage UAD. And let me say here apply law of addition of voltages. So always on the left we write the voltage that we are interested in calculating, which is UAD, and on the other side of this equation we go from A to D across different electric components such that we know their voltages. Then from A we can go to the point E because we know that UAE is equal to 25, and from E we'll go to the point D because we know that UED is equal to 3 volts. Then UAE plus UED, then UAE is given by 25 and UED is given by 3. So the value of UAD is given by 28 volts because 25 and 3 are expressed in volts. So the applied voltage UAD is equal to 28 volts. So UAD is equal to 28 volts. Now after that they are asking me about the voltage UCD. And this can also be done using the law of addition of voltages. So let's say apply law. Always in physics we need to mention the law that we are using. Apply law of addition of voltages. Always on the left we write the voltage that we are interested in determining, which is given by UCD. On the right hand side of this equation we'll go from C to D across different electric components. So from C we can go directly to the point B because we know the voltage UBC. From B to the point E because we know the voltage UBE, and from E to the point D because we know the voltage UAD. So let me say from C to B plus from B to E and E back to D. So notice that this is a valid equation because we have started with C and ended with D on both sides, and each letter we have inserted it twice. So now UCB, what's the value of UCB? Notice that here UBC is equal to 10, but we know that UCB and UBC are related via a minus sign, so in this case this is given by minus 10, plus the value of UBE is given by 5, and the value of UED is given by 3. So plugging this on the calculator, then the value of UCD is given by -8. Since all of these quantities are expressed in volts, then the value of UCD will be in volts. So UCD is equal to -8 volts. And now let me label this voltage on the electric circuit itself. We have that UCD is equal to -8 volts. Now after that they are asking me about the voltage UCB, but notice that we already know the voltage UBC, and UCB and UBC are related via a minus sign. Then we can directly say that regarding the voltage UCB, we have that UCB is equal to minus UBC. Recall that whenever we flip these points, we gain a minus sign, and the value of UBC from the electric circuit is given by tan. So this is equal to minus tan. Since this is expressed in volts, so the value of UCB will be expressed in volts. Then UCB is equal to minus 10 volts. Now finally they are asking me about UPN. UPN represents the potential difference across this DC voltage source, then the voltage UPN, and this can be done or calculated using the law of addition of voltages. Apply law of addition of voltages. So always on the left we write the voltage that we are interested in calculating, which is given by UPN. On the right hand side we'll go from P to N across different electric components such that we know their voltages. So here for example we can go from P to A to B, B to C, C back to N. So this is one example. Another one or another choice, we can go from P to A to E, E to D, D to C, C back to N. For example, another choice of a loop is given by P to A to D, D to E, for example, or D to C, C to N, D to E, E to B, B to C, C to N. But here we will choose the least path or the easiest path. So we'll go from P to A and A to B, B to C, and C back to N, such that we know the voltages across all of these electric components. So notice that I have started with P, started with P, ended with N, ended with N, and each letter we have inserted twice. Okay? So now across P and A we have a connecting wire. So this is 0, and the reason is given by a connecting wire. Now UAB is given by 20. As for UBC, it's given by 10. And the value of UCN across C, and then we have a connecting wire, and we know that the potential difference or the voltage across a connecting wire is 0. So here let me justify, because we didn't justify this previously, that UCN is equal to 0, and the reason is given by a connecting wire. So in this case, the type of this equation is a linear equation and one unknown. The unknown is UPN. So UPN is already placed on one side, and this is given by 30 after plugging it on the calculator. Since all of these quantities are expressed in volts, so the value of UPN will be in volts. Then we have that UPN is equal to 30 volts. So UPN measured from the positive to the negative is given by 30 volts. And now let me move to the next section, which is section number 4, which is identical components in series. So section number 4, identical components in series. So consider the electric circuit of the given document. We have a DC voltage source which is given by UPN, and we have two electric loads or electric components given by D1 and D2. Now suppose that D1 and D2 are identical loads. By loads we mean electric components, so identical electric components. So in this case we can say that apply law of addition of voltages So in order to determine, first of all, suppose that UPN is given. In order to determine the voltages UAB and UBC across the electric components, first we need to determine the voltage UAC across the two electric components that are in series. So we are interested in determining the voltage UAC. Let's place it on the left. And let's go from A to C across the battery or across the DC voltage source. So from A to P, P to N, and N back to C. And here in this case UAP is equal to 0, and the reason is given by a connecting wire. So let's keep UPN as a variable, and UNC is equal to 0, and the reason given by a connecting wire. So we have that UAC is equal to UPN. Okay, and this is reasonable because notice that the points A and C are in parallel with the battery. So here the first result is given by that UAC is equal to UPN. And now let me say the following. Since the electric components or electric loads are identical, then they have the same voltage. So the voltage UAB across the electric component D1 is equal to the voltage UBC across the electric component D2, which is equal to UAC divided by the number of electric loads that we have. So notice that here, because we have two electric loads, then we will divide by 2. So notice that B will be eliminated, and we have that UAC is equal to the number of voltages here we have, which is given by 2, 1, 2, and the value of UAC is equal to UPN, okay, divided by 2. So here if we have 3 electric components, then we divide by 3. If we have 4 electric components that are identical, we will divide by 4. Then we always divide by the number of electric components that we have, okay? And all of these quantities have the same unit because this is an equality between them. So let's consider exercise number 5 as a direct application on what we have explained now. They are telling me consider the two electric components D1 and D2 that are identical connected to a DC voltage source such that UPN is equal to 24 volts. So for sure they are talking about this document. Then the trick in solving this exercise is to label the voltage here. UPN is equal to 24 volts. Knowing that D1 and D2 are identical components. Now they are asking me to determine the voltage UAB and UBC across the electric components D1 and D2. So as a first step, in order to determine UAB and UBC, as we have seen previously, we need to determine the voltage UAC, and this can be done using the law of addition of voltage. So let's say apply the law of addition of voltages So always on the left we write the voltage that you are interested in determining, which is UAC. Why UAC? Because we need to determine UAB and UBC. Since they are identical, so B will be eliminated and we are interested in determining UAC. So UAC, let's go from A to C across the DC voltage source. So we have UAP plus UPN plus UNC. So across A and P we have a connecting wire which is 0. Let me justify here that UAP is equal to 0, and the reason is given by a connecting wire. Plus UPN, the value of UPN is given by 24. UNC is equal to 0 because across the terminals and NC we have a connecting wire. And in this reason the value of UAC is given by 24 volts. So, or in another way we can say that because the terminals A and C are in parallel with P and N, we can directly say according to law of uniqueness of voltages, UAC is equal to 24 volts. Now after we have determined the applied voltage across the two electric components D1 and D2, we can justify that since D1 and D2 are identical, then they have the same voltage. So we are saying that the voltages of D1 and D2, which are labeled by UAB and UBC, are the same, or they are equal, and this can be formulated in the following equation, that UAB is simply equal to UBC. So now how do we proceed? Simply we eliminate the points B, so this is given by UAC, dividing by the number of electric components we have, which is given by 2, because here we have 2 voltages, and the value of UAC we have already determined, which is given by 24 divided by 2, which is given by 12. Since this is expressed in volts, so this value will be expressed in volts. Then in this case we have that UAB is equal to 12 volts and UBC is equal to 12 volts. Then we have reached the very important section, which is section number 5, which is the electric potential difference. Sorry, electric potential reference. So let me write here the electric potential reference is a point taken on the electric circuit with 0 potential, and the symbol of this point is usually given by this. So it's very similar to the, so it's exactly the same to the symbol of the ground or mass terminal of the oscilloscope. Okay, so let's suppose that in this case the point B is chosen to be the reference electric potential or electric potential reference. So here on the electric circuit I will label the point B to be the electric potential reference, like this. So usually these legs are tilted. Okay, then let's say suppose B is taken as electric potential reference. So by reference, it means that the thing that we refer to, by definition here they are telling us that this point is defined to be the zero potential. So let's say since B is taken as a reference electric potential reference, they are the same. Then we have in this case that VB, the potential at the point B, is equal to 0. So notice that here we can talk, for example, about the voltage UCB, but whenever we specify the voltage across a point, we mean the electric potential and not the electric potential difference, okay? So what's the important or the reason behind taking a point to be an electric potential reference in a given electric circuit? Now we can determine the electric potentials at other points, say for example the point C, the point A, the point P, and the point N. So suppose that here in this circuit we have that UPN is, say for example 10 volts. So UAB will be given by 10 volts. Let's suppose that this is UCB is equal to, say for example 6 volts. Then UAC according to law of addition of voltages will be given by 4 volts. Suppose that we are interested in determining the electric potential at the point C. So we are interested in determining the electric potential at the point C, which is given by Vc. So in order to determine the electric potential at the point C, we need to know the voltage that relates this point to another point. In such a way, we know the electric potential at the other point. So say for example, if we consider the voltage UCB, so we are moving from B to the closest point. So UCB in this case is equal to 6 volts. Notice that we are interested in determining the potential at the point C, which is Vc. So Vc can be extracted from this because we know that UCB is equal to Vc minus Vb. Now this is equal to 6. We are interested in determining Vc. So in order to determine Vc, we need to know the value of Vb, because Vb is taken as an electric potential reference, so Vb is equal to 0. Now Vc minus 0 is equal to 6. So what's the type of this equation? This is a linear equation and one unknown. The unknown is given by Vc. So in this case, Vc is equal to 6. Since 6 is expressed in volts, so the value of Vc will be 6 volts, okay? Now if you consider also another example, suppose that we are interested in determining the potential at the point A, which is Va. So let's say electric potential at A. So, okay, we are interested in determining the electric potential at A, Va. So in order to determine the electric potential at A, first of all, we need to think of moving to the closest point to the point A. So we need to know the voltage, we need to know a voltage U such that it includes the point A and another point in such a way that we know the voltage and we know the electric potential at the other point. Say for example, if you consider not the point B, if you consider UAC, okay? So here we have UAC is equal to 4 volts. Now the electric potential at the point A can be extracted from this because we know that UAC is given by VA minus VC is equal to 4. We are interested in determining VA. We know the value of VC to be given by 6 volts. So VA minus 6 is equal to 4. So what's the type of this equation? This is a linear equation and one unknown. The unknown is VA. So VA is equal to 4. Dragging minus 6 to the right hand side, we have plus 6, so it's equal to 10. Since both 4 and 6 are expressed in volts, so the value of VA will be in volts. So VA is equal to 10 volts. Okay. So for example, we could have also calculated the potential at the point A by using the voltage UAB. Okay, and so on and so forth, as we shall see in the coming exercise. So this is the importance of taking an electric potential reference. Now let me mention also the following. So what about the same electric potential? So let me write any two terminals connected by connecting wire have the same electric potential. Now this also, okay, this is independent of the reference electric potential. So here what I'm saying is that any two terminals connected by connecting wire have the same electric potential. So suppose here, if you consider the points P and A, we know that UPA is equal to 0, and the reason is given by connecting wire, which means that VP minus VA is equal to 0, which means that VP is equal to VA. Okay? However, we can use this result directly by just mentioning the reason, which is given by connecting wire. So here, for example, the terminals B and N are connected by a connecting wire. So we can say that VB is equal to VN, and the reason is given by a connecting wire. Without going through this justification. Okay, so we can directly say that the potentials at B and N are equal, and the reason is given by connecting wire. Now let me also explain the following. So higher or lower electric potential So suppose that here we have that UAC is equal to, say, for example, 16 volts, okay? So independent of what are the values of UPN, UAB, and UCB. So let's say that UAC is equal to 16 volts, and suppose that we put forward the following question: which terminals A or C has higher electric potential? So here the question they are asking us, which terminals A or C has higher electric potential? The electric potential is denoted by V. So by higher means greater. So we are asked to compare the potentials at the point A and the point C. Suppose that we don't know the values between VA and VC. So here we need to compare. We need to say if one is greater, less than, or equal. So suppose that if we don't know the values between A and C, we can compare the electric potentials between these 2 points by simply knowing the voltage that relates these 2 points, which is given by 16 volts. So if UAC, so here let me say that this is the answer. So UAC is equal to 16 volts, and we know that the electric potentials VA and VC are encoded in UAC, and they are given by VA minus VC is equal to 16. Notice that here 16 is a positive number, so which means that VA minus VC is positive, which means that VA is greater than VC. Now let me say, since VA is greater than VC, full point, then the electric potential at the terminal A, or let me say the terminal A is has a higher electric potential, But compared to which point? Compared to the point C. Because notice that we can compare the potential A to the point P, to the point N, to the point B, to any other point, but here we are comparing the terminal A to the terminal C. So the terminal A has a higher electric potential compared to C. Then exercise number 6 is a direct application on what we have explained previously. They are telling me 3 electric loads are connected to a dry cell of voltage UPN is equal to 9 volts. Then let me label this voltage here. UPN is equal to 9 volts. As shown in the adjacent figure, so they mentioned the figure, now we can use it. They are telling me the two loads D2 and D3 are identical, so this is important. Then number 1, they are telling me indicate with a justification. Indicate by itself means that we need to specify with a justification. Part A, which terminal P or N has higher electric potential? And here by the electric potential they mean V. So which terminal P or N has higher electric potential? Higher means greater. So in other words, we need to compare the electric potentials at the point P and at the point N. So we need to say if one is greater, smaller, or less than the other. In order to do so, we need to know the values of Vp and Vn. Notice that at this till this moment we don't know the values of Vp and Vn simply because we didn't choose yet a reference electric potential, since they didn't mention in the exercise anything about the electric potential, reference electric potential, although it's specified here at the point P. However, another way in order to compare the values, the electric potentials Vp and Vn, is by determining the voltage that relates these 2 points. So we can say that UPN is given to be 9 volts, and we know that UPN is given by Vp minus Vn. So in this case it's equal to 9, which is a positive number. So Vp minus Vn is positive. So dragging Vn to the right hand side, it will gain another minus sign to be positive. So Vp is greater than Vn. So let's say since Vp is greater than Vn, then the terminal or the point P has higher electric potential compared to N. Okay, so the terminal P has higher electric potential compared to N. This is important. Why? Because here we can compare the potential P to any point of this electric circuit, or to any terminal, to the point A, to the point C, to the point B. Okay, so it's important to mention at the end to which point we are comparing P, which is the point N. So Vp is greater than Vn. Now in part B, they are telling me which 2 terminals have the same electric potential. We know that any 2 terminals connected by a connecting wire, they have the same electric potential. So here, for example, P and A, between P and A we have a connecting wire. So we can say that P and okay, so Vp, okay, since Vp is equal to Va, and the reason is given by a connecting wire, then the terminals P and A have the same electric potential. But not only the points P and A, notice that here the points N and B are connected by a connecting wire. So we can say that since V at B is equal to V at N, and the reason is given by a connecting wire, then the terminals B and N have the same electric potential. Now notice that here we can add infinite number of points. For example, here we can add the point M and say that the points A and M have the same electric potential, but we restrict our answer to the points labeled on the given electric circuit. Okay, for example, we can consider another point here E, and we say that A and B have the same electric potential, or here the point K, for example, and here X, etc. But we will only restrict our answer to the points labeled on the electric circuit itself. So this is it for number 1. So let me write here. Okay. Now as for number 2, they are telling me to determine the voltage across each load. So the loads in this electric circuit are given by D1, D2, D3. So in other words, we need to determine the voltage UAB, the voltage UAC, and the voltage UCB. So here, since they didn't specify which voltage we want to calculate, okay, so for example, they are specifying these voltages across D1, D2, D3. We can say, for example, UAB or UBA, but since they didn't specify which voltage, we are free to calculate either UAB or UBA, but we will choose by default to calculate UAB, UAC, UCB, knowing that if the direction of the electric current is like this, so all of these voltages will be positive. So let's start by the voltage. Okay, so the voltage across D1, which is given by UAB. So we can say that D1 is in parallel with the battery, so they have the same voltage according to law of uniqueness of voltages. But another elegant way to calculate it using the law of addition of voltages. So apply law of addition of voltages. So in this case, we are interested in determining UAB, so let's place it on the left. And on the other side of this equation, we'll go from A to B across different electric components such that we know their voltages. So we'll go from A to P, P to N, and N back to B. So notice that I have started by A and ended with B on both sides, and each letter I have inserted it twice. So UAP is equal to 0 because across A and P we have a connecting wire. So let me justify here that UAP is equal to 0, and the reason is given by connecting wire. Now UPN is given by 9, and UNB is equal to 0, and the reason is given by that across the terminals of N and B we have a connecting wire. So this is 9 plus 0. So this is a linear equation and one unknown. The unknown is UAB, so this is given by 9 volts. So UAB is equal to 9 volts. So as we have said previously, that it's important to label the voltages with their names or labels on the electric circuit itself. Now it's left to determine the voltages UAC and UCD. So notice that here we have two unknowns. However, recall that the two loads D2 and D3 are identical. So in order to determine the voltage across D2 and D3 respectively, we need to determine the voltages across their terminals combined, which is UAB. Already UAB is given by 9 volts. So let's say since D2 and D3 are identical, then they have the same voltage. Their voltages are given by UAC and UAB. So we are saying that UAC and UAB, this when we say then they have the same voltage, then this can be formulated by an equal. So we have that UAC is equal to UAB, sorry, UCB. Combined, we can eliminate C, which stands for UAB, which is the applied voltage across their combined terminals, which is given by UAB, and we divide simply by the number of loads we have, which is given by 2. The value of UAB is given by 9 divided by 2, which is given by 4.5. Since 9 is expressed in volts, so the value of each will be expressed also in volts. Then UAC is equal to 4.5 volts, as well as UCB, and let me label these applied voltages on the electric circuit itself. So here we have that UAC is equal to 4.5 volts and UCB is equal to 4.5 volts. So this is it for number 2. Now in part 3 of this exercise, they are telling me the terminal B is taken as an electric potential reference. They mentioned the electric potential reference, which is noted here. Calculate the electric potential at each terminal in this circuit. So what are the terminals of this circuit? They are the terminals B, C, A, P, and N. So simply we are interested in determining the potentials at the point B, electric potentials at the point B, C, A, P, and finally N. Okay? So first we always start by the reference electric potential or the electric potential reference, which is taken the point B. We know that always whenever a point is taken as an electric potential reference, then VB is equal to 0. So let's say since B is taken as an electric potential reference, then VB is equal to 0. So what's the unit of V? V is expressed in volts, but notice that 0 multiplied by anything is 0, so no need to write here the unit. So here we have that VB is equal to 0. So we are done with the point B. Now let's move to the closest point to the point C, let's move to the closest point to the point B, which is the point C. So we are interested in determining, let me here write. Okay, so we are interested in determining the electric potential at C, which is given by Vc. Now in order to determine the electric potential at the point C, we need to know the voltage that relates this point to another point in which we know the electric potential at that point. So if you consider UCB to be 4, which is given by 4.5 volts, we know that UCB is given by Vc minus Vb, and in this case it's given by 4.5. Knowing that we are interested in determining the electric potential at the point C, which is given by Vc, in order to determine the electric potential at the point C, we need to determine the we need to know the electric potential at the point B, and in this case it's given by 0. So Vc minus 0 is equal to 4.5. What's the type of this equation? This is a linear equation, and one unknown, the unknown is Vc. So simply Vc is equal to 4.5 volts. So let me write here that Vc is equal to 4.5 volts. So we are done with the point C. Now let's move to the closest point to the point C, which is the point A. In order to determine the electric potential at the point A, we need to know the voltage that relates this point, which is the point A, and to another point in such a way we know the voltage and we know the electric potential at that point. So let's consider the point C, because we know the voltage AC to be given by 4.5 volts and we know the electric potential at the point C. So let me write here electric potential at A. Then we will consider the voltage UAC, or the electric potential difference, which is given by 4.5 volts. We are interested in determining the electric potential at A that is extracted from this equation, which is given by VA minus VC is equal to 4.5. Now we are interested in determining VA. In order to determine VA, we need to know the value of VC, which is previously calculated here to be given by 4.5. Now what's the type of this equation? Linear equation and one unknown. The unknown is VA. Then dragging minus 4.5 to the right hand side, VA is given by 4.5. So this, dragging it to here, it will be plus 4.5, which is given by 9. Since both of these quantities are expressed in volts, so the value of V will be expressed in volts. Then the potential at the point A is given by 9 volts. Let me make some space here. Now let's move from the point A to the closest point to the point A, which is the point P. Here we are done with VA. Let's move to the point P. Notice that between A and P we have a connecting wire, as we have done in one part B. We have mentioned that they have the same electric potential. So we are interested in determining the electric potential at P, which is given by Vp. Here simply VA is equal to Vp, and the reason is given by connecting wire. But we know that the value of VA is equal to 9 volts, so Vp is equal to 9 volts as well. Now we are done with the point P, so it's left to determine the electric potential at the point N. So moving from P to the closest point, indeed, which is the point N. So in order to determine the electric potential at the point N, we need to know, so electric potential at the point N, we need to know the voltage that relates this point to another point in which we know the electric potential of the other point. So if we consider UPN, we know the voltage between these 2 points, which is 9 volts, and also we know the electric potential at the point P, which is 9 volt. So electric potential at N, so we have that UPN is equal to 9 volts. Now we are interested in determining the electric potential at point N, and it can be extracted from this equation here, because Vp minus Vn, now in this case it's equal to 9. We are interested in determining Vn, and the value of Vp is given by 9. So 9 minus Vn is equal to 9. What's the type of this equation? This is a linear equation and one unknown. How do you solve this equation? We drag Vn to the right hand side and drag 9 to the left hand side. We have 9 minus 9 is equal to Vn. So eventually Vn is equal to 0. And no need here to place the unit, okay? So Vn is equal to 0, and this is expected Y. Now in order to determine the electric potential at the point N, we need to consider the closest point. Here we have two choices. Either we consider the point P, because we know the voltage UPN, or we consider the point B. Now we know that B is chosen as a reference electric potential, so VB is equal to 0, and VB is equal to Vn, because we have a connecting wire. So if VB is 0, then Vn is equal to 0 according to this equality, and as we have calculated here, that Vn is equal to 0. So that's it for me in this video, guys. In the next part, we'll complete solving exercises on this chapter.